CLion, a cross-platform IDE for C and C++. Download now.
So we're going to talk about how to choose the right container in C. See, I got this wrong. How to choose and use the right container in C++ 26. But I was running out of space, so. Hello? Okay. So I may stop for a few questions, but I've got a lot to get through. Definitely take more at the end. If we don't get to any, just come find me. I'm here all day. We're going to talk about C++. If I talk about current C++, I mean 23. I realize not everyone's got 23 yet, sadly, but it is the most recent. If I talk about upcoming C++, it will be 26, because we pretty much know it's going to be in 26 at this point. And specifically, we're going to talk about standard library containers. Who am I? I've been programming a long time. I've been using C++ for 35 years, and I've been on the C++ committee for 20 years. Ugh. But why? Why talk about containers? I mean, everyone knows about containers. Everyone uses containers. They've been talked about. They've been written about. Why are they interesting still? To me, they're interesting because of performance. If you don't use them right, they can have terrible performance. But if you do use them right, they have great performance. And in fact, the reason we have so many different containers is because they each have a different performance profile. That's really almost the only reason we have different containers. You really could just use vector if you had certain pretty limited. I mean, there are some things you can't do with vector, but it's mostly performance. So you have to understand how performance of containers works. And you'd think that this would be common knowledge, but I've discovered that it's really not. It's less well known than you'd think it should be. In fact, people who should know better don't know things like, oh, I don't know, me. I recently learned something, which we're going to talk about in a bit, that I didn't know, and I should have known. And it actually would have made a difference for the project I was working on. The standard library, the design of the standard library, the API, as John, who's sitting right here, spoke about very eloquently yesterday. If you haven't seen his talk, zip back in time to yesterday and go see it. The design gives us hints about how to use, or in some cases, not just hints, mandates about how to use the standard library. Unfortunately, those are misleading in some cases, and we're going to talk about why. So, performance. What is performance? I'm going to go through this pretty quick because this has been talked about. Matt Roper gave a great talk on Tuesday. Again, use the time machine, cut right back here. That covered a lot of this stuff in great detail, which is great, especially about allocation and deallocation. But the thing is, as we probably know, accessing main memory can be over 100 times slower than the inner cache. Computation speed has increased a lot, but memory speed has not. And so modern systems make up for that by using very large caches. And modern memory, I just learned this myself, actually, from, I can't say it right, I'm sure, Fedor Pikas's C++ Now talk last year, that modern memory trades latency for bandwidth. They want to get more over faster, and to get to that, they actually increased latency over earlier chips. So if you defeat your cache, cache, right? I'm in England. As cache? Oh, okay. Someone I was watching was calling it cache and saying, oh, I really should call this cache, but we call it cache. Okay. Thought it was a British thing. If you defeat it, you're going to run slowly. And locality of reference is really critical, more so than ever. So one might have thought, oh, these problems are going away because hardware is just so amazing, which it is. But no, it's actually getting worse. You need high efficiency density to be efficient. My friend Howard gave me that quote, and I think it's a good way to put it. So this means that size matters. Big is slow. The more stuff you have to get to out in main memory, the slower things go. If it fits in inner cache, things go really fast, which means that for small data, computation tends to dominate. But for large data, eventually memory access will dominate your program. Order matters. So if you're storing, let's say you're storing an array by row, so in row major order. If you access it in column major order, you get a 10 times hit because of having to keep going out to memory. But the prefetch helps you with that because you have a fixed stride. If you have random access, prefetch can't do anything with that. And that gives you another 10x hit. So you get a 100x hit over accessing contiguous memory. And it's very difficult to profile memory cost. Your profiler says, oh, you're spending time in this function, but it doesn't actually tell you whether you're spending time computing or waiting for data. So we know what containers are. They hold stuff. Some things aren't containers, like strings. They hold stuff, but they're not a container. Not technically. We're going to focus on the behaviors that affect performance, the big picture, not on details of how to build good containers. This isn't a tutorial on that. Your library will differ. These are caricatures in a sense to make a point. And we're not going to talk about things that are very important, like for instance, custom allocators, right? You can do all kinds of amazing performance things with custom allocators. How many people here have ever written a custom allocator? Hand. Not too many, right? I have not. You see, my hand didn't go up. So I'm talking about what you get out of the box. In the box. You know what I mean. So we're going to start with the contiguous sequence containers. Everything's all in one block. You get the best iteration performance, the best locality of reference. But there's an issue, which we're going to talk about. So we have to spend a moment here on array and C arrays. So let's actually do that. We know what these are, right? Everyone knows this stuff. They're local only, fixed size, therefore obviously fixed capacity. I consider these aggregates, not containers. The array, standard array is in the containers chapter of the standard, but it's not really a container. It's an aggregate with some container convenience features. So we're not going to talk about these. Don't get me wrong. Standard array is great. You should use it, but it's not. The memory issues aren't confusing. Let's put it that way. So we'll start, of course, with vector. Vector's the go-to container. Everyone says this. We heard about that from John yesterday. Both Alex and Bjarne, right? Vectors keep everything in this single block. It's got order one insertion if there's room. Otherwise, you got to get a new block, move everything over. Deleting the elements or calling clear doesn't deallocate your block. This is important. Remember this. The block is deallocated, of course, when the vector is destroyed. Or you can call shrink to fit. And if the vector is empty, it will deallocate. So to visualize this, I kind of like to think of it as a lifeboat. And our elements are swimming along, hoping to get in the lifeboat. And they all want to go to the front. So the elements come along. Okay. What happens now? Uh-oh. Problems. We got to get a bigger boat. And then we got to wait while everyone moves down. And finally, whew, okay. And then we can finally get rid of the old boat. So when you run out of room, you need a lot of available space, right? I wrote these slides based on a 50% or 1.5 growth factor, which is what Microsoft uses. A couple other libraries use 100%, 2.0. The same issues, slightly different numbers. You need a lot of room, because you need the new one and the old one to coexist. So theoretically, in the perfect world, you can't grow a vector larger than 3/5 of your memory if you're using 50% or 2/3 if you're using 100%. But in practice, it's never going to be anything like that, right? Because you've got other things going on, you've got fragmentation, you're not going to hit those numbers exactly. You can't fill memory with a vector. It's just, unless you know how big it needs to be at the beginning of the program and you reserve the whole thing then, which isn't practical if you have lots of vectors. I mean, it could be, but it's typically not practical. And of course, growing is expensive because you got to move, copy, and moving and copying or copying is going to dominate for large sizes. And don't think move's going to save you here. There seems certainly for a while to be this idea that, oh, well, we have move, so no problem. Most things you put in a vector are not going to differ when in performance, moving versus copying. I mean, even so string, right? String has resources, it has move behavior, that's awesome. Let's say you have a vector of strings that's holding last names of your organization or whatever. How many last names are longer than 15 characters, right? Move and copy are going to be the same because string has a short string buffer of 15 characters. You're always going to be copying that. You can reserve to avoid some thrashing. So let's look at this. This is the basic memory picture of vector. I'm sure everyone here knows this. Very simple, nice light object, just 3 pointers. But how did we get here? Well, okay, we start out with nothing, that's great. We put in one element, we have a block that's 1 element long. Multiply that by 1.5, well, you can't grow by less than 1, so that means we're going to go to 2. Multiply that by 1.5 and put in another one, we go to 3. Now 3 times 1.5 is 4.5, but it rounds down, so again, another allocation. These are all allocations, deallocations, super slow. Finally, at 5, you get 1 extra slot. And so until you start getting into larger sizes, you're just thrashing. So what can we do about this? We can pre-reserve 8, let's say. Now we can just fill it up, right? Without all that thrashing. But although this helps, depending on your situation, this is not really the problem. So because of the way vector grows, it develops what you might call a capacity history. I think I got that term from Howard too. So after a while, the capacity will be the largest required for the job. So let's say you're using a bunch of vectors and you're putting stuff in them, taking them out. They'll tend to grow until they're the right size and then just sit there, okay? You may not know ahead of time what that is, so you can't necessarily pre-reserve that. Because after all, if you pre-reserve too much, that has its own costs and problems. So if you clear the vector, the capacity history is retained, right? Because it doesn't deallocate the block. But if you destroy the vector, the block goes away. So what happens if your vector's inside a loop? So good programming practice, you're going to put declaration right where you use it. Maybe you're even gonna, who knows, declare it and pass it to a function. Pass it as an R value to a function, who knows? The point is that the scope of the vector is in your loop. You're gonna be creating all this memory, deleting it, creating it, deleting it, every time through the loop. And depending on how well you can pre-reserve, you're gonna have to climb back up those logarithmic steps to get to the size every time. So if you're doing this all over the program, or a bunch of different functions are doing this, and there's a lot of vectors living at once, it gets much worse because of fragmentation. So after all, vector growth creates fragmentation, right? It gets bigger and bigger. You keep deleting, you leave these holes. And it's also much harder to spot this is going on in the code. So, and by the way, Matt Roper's talk on Tuesday talked about this problem. So I unknowingly did just this when I was working on a simulator. So the simulator used a bunch of temporary vectors to hold things. And I discovered that the runtime was increasing by a factor of 100 when the number of steps increased by a factor of 10. Oops, something's wrong. So I profiled the time was being spent in the vector allocation, but I was doing everything right. I was reserving. I was being careful to move things. What was going on? I think we can see the problem, right? I was thrashing the heap with all these vector creations and deletions and growths. So what's a solution? Well, if it's a really simple case, you could just hoist the vector out of the loop. But most cases you're going to run into aren't that simple. And you don't want to pass the vector down into something just in order to get this behavior. That's not really very good design. So better approach, recycling. Right? Put the dead vectors into a container which holds them until you need them again, the recycling bin. So I used this technique, and the runtime went down from 7 hours, 15 minutes, to just over half an hour. My customers were really happy about that. This was game-changing, right? And it was very simple to implement. So this is an extraordinarily simplified example, but this runs and works. So you can use this class all over the place. I mean, obviously it would be a template, whatnot. I just did this with ints, but if there's nothing in the recycling bin, we're just going to do some sort of intelligent reserve, if we can, and we're off and running. When we're done, there's some way to point. I'm not going to bother. You can see the destructor here. When we're done, we're going to clear the vector, and then we're going to throw it in the recycling. We're going to move it into the recycling static vector of vectors. And then when another one pops up and is constructed, there's something in the recycling bin, we'll just move it back into our local one. Works great. Very simple. Just don't forget to empty your recycling once a week out by the street, because obviously you're holding memory, and if you're done with it, you want to let go of it. Now we get to vector bool. Yes, this is, I think, as far as I know, the most famous blunder of the standard library. It's been around forever, and it has been evoking something ever since. One of the reasons I wanted to talk about this is that, I tend to like everyone I know, or everyone I talk to about C++ knows this, right? But this isn't necessarily known, and I think it's important to talk about it. There was a paper, this came up on the C++ committee's reflector, email reflector. There was a paper published by somebody, and they were doing some analysis of some algorithm, and they compared across several languages, and they needed a vector of Boolean bytes, okay? And they did this in several languages, and they used a vector of bools, expecting a vector of bools. What were they thinking? And guess what the performance comparison showed? Guess how C++ did? Right, terribly. Because, and this had nothing to do with C++, right? And you can't blame the authors, right? Why would any sane person think that of all the types in the world, bool does something completely different? So, what are the problems with bool? It's not a sequence container because it's not a container, not technically. Doesn't meet the requirements. And it can't meet the requirements because, for one thing, you can't have a reference to a bit. And of course, it's also not a vector of bools, which, you know, as I've said, is a little bit misleading, to say the least. Mind you, a bit set's a very useful data structure, and a bit set can save you space and time, a proper bit set. It's not about bit sets. Vector bool just isn't a very good bit set. And this is because most of the libraries don't have specialized algorithms. Now, there is an exception. libc++, I gather, does, probably due to Howard, but most of them don't. And as I'm sure I don't need to explain, accessing bits individually is a huge pessimization. And, you know, it doesn't fit well into a vector. It was shoehorned into vector instead of properly implemented as its own class. So what do you do? Well, the standard library has a bit set, and it's called, amazingly, standard bit set. It's a static bit set, however. If you want a dynamic one, Boost has one called dynamic bit set. If you really want a vector of Boolean bytes, you can do something like this, unit 8 or whatever you want to put there. Just don't use bool, because you probably won't ever get what you want, never mind always. All right. Let's go to some good news, something more fun. In-place vector is a new upcoming edition. By upcoming, I mean C++ 26. This provides a local contiguous sequence container. And I don't think I mentioned this before, but by local, I mean not out on the heap. I mean on the stack, embedded in an object, in global memory, in registers, but not dynamically allocated. So it's just like Boost static vector, if anyone's familiar with that. So the elements are embedded in the container object, also has a size. Capacity is fixed at compile time. Otherwise, it tries to be a vector as closely as possible. And because it doesn't allocate memory, all of these things we're talking about aren't a problem. It can have dramatically better performance if you can use a fixed capacity container. You can even choose what you want to happen when you exceed the capacity. You can throw, you can return a null pointer, or you can crash, or UB. What is it that it does? It lights, the dragon comes out and burns off the keyboard. I like that slide. I wish I had that slide. Yeah, anyway, emails your boss, tells the message that you're quitting, you know, whatever. So you get to choose. So, you know, just because I want to give pictures of everything, pretty obvious what it's going to look like. You got a size, here come your elements. You got a fixed capacity of 5, try and put in a 6th, and you get, you know, whatever. In-place vector is great. Coming to compilers near you soon. This one is a proposal. It's not yet anything other than a proposal that's not at the moment active. But despite the sort of dowdy name, This is actually boost small vector. It's a small buffer optimized vector. This is also something we really want. We're going to come back to this at the end when we talk about sequence, which is something we're going to talk about at the end. It offers vector, in place vector, clump, and other behaviors. We'll come back to this. Again, this is a proposal. All right. Let's talk about block-based containers. I mean, in a sense, they all have blocks, but we're talking now about containers that may have more than one block. These offer good iteration performance because the iterator is mostly just iterating contiguous memory. It does have to have a branch to tell whether it's got to the end or not. But, and I'm stepping out of my comfort zone here. I'm not a hardware guy, but the branch prediction ought to be pretty good because it's always false, right, till it's not. So iterates well. Excellent locality of reference if your blocks are big enough to make that so. So let's talk about them, starting with DEC. So DEC is short for double-ended queue. In fact, some people call it a DQ, I think, or DEQ, something like that. And the DEC keeps elements in dynamically allocated blocks. But DEC's much more interesting than just the fact that it's a double-ended queue, and we'll see why in a minute. So the blocks are managed by something that is known internally to the DEC as a map. This is confusing if you actually look into the code because it's not a standard map. It's not even an associative array at all. It's just a vector, or if you will, an array of pointers to blocks. And how it's managed differs from implementation to implementation. In fact, one of the themes of my discussion of DEC is the design of all this is implementation defined, and the implementations differ dramatically in how they do DEC. We're going to get back to that. Order one insertion if there's room. If there's not room, you get a new block that nobody's moved. So that's really nice. Deleting the elements may or may not, all the elements in a block may or may not free it. That depends on your implementation. But what's really great about DEC is it offers fine-grained linear memory growth, right? You can fill memory up with it. Vector, because it's exponential, you can't. We've seen that. So, but with DEC, because the blocks are the same size and they don't get very big, you can fill memory right up with them. Works great. This is much more important, in my opinion, than the fact that it's a double-ended queue. And the growth doesn't cause fragmentation because nothing's ever deallocated if you just keep growing. Unfortunately, you can't control the block size, and that is a drag because you'd like to be able to tune that if you are, in fact, trying to fill up memory. Remember this, that you'd like to be able to tune that. And some libraries have absurdly small block sizes. We're going to see what happens, how that affects your life or my life, how that affected my life in just a minute. Nonetheless, this is a really good reason to use DEC because nothing else in the standard library has these properties. The only other thing you could use is something like a list, which fills memory with beautiful precision, but is incredibly slow for reasons we'll discuss later. DEC has random access and iterations fast and good locality reference. What's not to like? So we'll just look quickly at how this might be implemented. Again, this is a caricature. I mean, I'm clearly missing something because there's nothing hanging on to the beginning and end of the map, but you get the idea. So we got one element, two elements, three elements. Now what happens? I dropped the extra arrows just because it would get too confusing. They're meant to still be there in your imagination. Let's add to the front again. We get a new block for the front, and we start adding to the back of it. Yeah. And we want to add to the back. We get a new block for the back, and we start adding to the front of it. That's basically what a deck does. Groovy, yeah? But unfortunately, it's time for our first misdirection interlude. For small sizes, deck is awful, right? You can see why. It's got this big map structure. The blocks, if they're reasonably sized, might be, if you have a list that's got 10 elements and the block, default size is 256 elements. I mean, there's all this overhead. And locality of reference and iteration are good, but they're not as good as something like a vector. Vector, on the other hand, does not have any front operations. Now, you can put stuff in the front of a vector using insert, but the fact that it doesn't have push front and pop front suggests that maybe you shouldn't, right? This is the message that, as we learned, Alex is giving. You shouldn't do that. That's bad. Don't do that, okay? And in fact, as we're gonna see, Q insists that you have those, so you can't even use Q with vector. But for small sizes, vector's in inner cache. If you've got I've tested this. I've got links at the end. Everything's linked at the end, including a talk of mine where I'd give some numbers for this. If you push stuff at the front of a vector, and for small vectors, and I'm talking small like 100 even, it goes way faster than a deck, and certainly way faster than a list. So it doesn't make sense not to do these things. The fact that the theoretical complexity of pushing front on a vector is n does not mean that it's slow, right? Unless, of course, your vector has a billion ints in it, in which case, yes, it's slow, okay? So what happened? So I needed to log lots and lots of small records in the simulator. That's the simulator's job, is to generate data and hang on to it and then burp out a huge pile of reports based on the data, okay? And it needs to happen without slowing the simulation down. These logs are always growing from the back, right? They needed to be quickly iteratable. The user gets to control how much memory is plugged into the computer and how long to run a simulation for. It's not up to me. So I have to be prepared to fill memory up with these things, or the user's going to get upset. So how should I store these logs? A vector's super fast, but as we've seen, the growth requirements make vector not viable. A list will fill up memory very nicely, but as we're going to see, is extremely slow. But a deck doesn't seem to fit the pattern, right? I mean, we don't need a double-ended queue for this. So what should I use? Don't all speak at once. Right, deck. It's fast to insert. It has everything you need. And that's what I used. Not because I didn't care. I never inserted at the front. I just cared about filling up memory nicely. And it worked well enough. But there was something I did not know about deck, specifically the Microsoft deck. So this was a surprise, and I just learned this recently. So the Microsoft deck is a very strange implementation. And I'm not picking on Microsoft. I'm getting this from the article that one of their bright guys wrote about this and published. It's a Microsoft article. So for my situation, my block size was 1, okay? So I didn't have a deck anymore, right? I had a node-based container. In fact, what I had was an array of pointers to nodes, but it might as well have been a linked list. Same basic performance profile. So I did a little test, and sure enough, I filled the deck with some little things, and then I filled a vector of vectors with the same little things, over 4 times faster. And I was looking at this slide last night, and I realized I didn't actually check the iteration, and I should have, because I bet the iteration would have been pretty dramatic too, because of the locality of reference problems. I will check that someday, but I didn't. But I bet that would also be a lot slower for the deck. And I tried a list, and sure enough, it was only a little bit slower than the deck. It was the same, very close, the same order, certainly the same order of magnitude. So check your deck, trust but verify. And because of this great article from Microsoft, you can check the 3 most common libraries, because he gives a complete chart of what they do and how they do it. Yes?
Strange question.
No, that's, oh, hello, there we are, thank you. This might seem a strange question, but would you have thought about implementing your own deck?
Well, the question was, would I have considered implementing my own deck? I didn't, because I thought the deck was, I didn't look into it. I didn't consider the deck might be a problem. Now, I might, yeah. But I also might just, for this particular case, I might actually use this technique, a vector of vectors, which is pretty similar. And I get to control the sort of, I can tune it where I can't tune a deck. Isn't there an album like that? Something about it. Can tune something. So I might, but I might also use parts that I already have, like vectors.
This seems like a very odd choice for the implementation. Did this article tell you why, or did you contact STL and ask him what he was thinking?
I don't think it was STL. I think this predated him. The article is by, well, we'll see at the end. You probably know who I mean. I forget his name, but he's great. But it wasn't an STL article. But I suspect this predated him, and the tone of the article was, in effect, this really stinks. I think they're going to fix it. But as of the latest version of 2022, I guess I'm on, it isn't fixed.
That seems like evidence the deck is not widely used.
Right.
Because certainly people would have
Right.
discovered this.
So I hope I'm going to fix that today. Use deck. It's awesome. Yell at Microsoft. Maybe I'll yell at STL. That's the nickname of and the initials, ironically, of the guy who runs the what?
No, it's from saving videos, saying to STL.
Yeah. I'm not going to try and pronounce his name. It's Lawawa, I think. Lalaway?
So,
Lalawade. Lawawalade. He himself says that it's a banana problem. As in, I know how to spell banana, but I don't know when to stop. That's STL's joke. Yeah, he's a completely awesome guy. Okay.
Sorry, before we move on, can I ask a question about deck? You mentioned that you can't really control the size of the block. Even if you add some sort of custom allocator, you still can't control the size of the block. So there is absolutely no specification of the deck that allows you to control the size of the block.
Right. Deck does not let you control the size of the block. It's implementation defined. Was that your question?
Yes.
Okay. Yes. But don't completely despair. We're going to talk about a container later that gives you control over things. Unfortunately, it's not a deck.
Okay, I'll
But
keep my hopes.
maybe we'll get there. Deck 2.0, because it should, right? I think you should have control over the things you'd like to have control over, like the block size and how many blocks you expect. Okay. So, how are we doing? Eesh. All right. Why isn't this? Another new container in C++26. It's called Hive. Used to be called Colony. Do not ask me, please, where these names come from or in what sense these names are related to what it does. I don't know. Ah, Guy does. If we have time, I'd like to hear that. Let's get to the end and then remind me. So there's still a colony project. Hive, the standardized Hive has diverged a bit from the original colony, but it's a specific implementation of a more general data structure that's been around for a long time, sometimes called a bucket array or an object pool. It's a block-based container. The implementation, the reference implementation, this hasn't been implemented by any libraries yet, but the reference implementation or example implementation is does not use an index to the blocks. It uses a double-linked list of blocks. If the blocks are full, you get a new block that's bigger, and the expansion factor for the reference implementation is 2.0. The blocks can have user-defined mins and max sizes, so that's nice. You get some control there. What's unique about this is that, I mean, one of the main thing, I guess, that's unique about it is that when elements are deleted, nothing is done about the hole that they leave. It's kept in place, and it's remembered, and it's reused. So we're going to look at how this works. So Hive, because of this, offers a very unique collection of features, unique in the standard library. You've got order one insertion to an unspecified position, because as you see, Hive is unordered and does not support random access. Right? So unless a new block has to be created, order one to insert, order one to delete anywhere. And an implementation might throw out an empty block, or it might not. But if it did, of course, then if it were doing that when you did a deletion, it would cost something more. But the reuse of space freed by deletion, stability. One of the main issues here is that your elements are always stable, but you have fast iteration and pretty good locality of reference. So no other container in the library does all these things at once. It's ideal for use cases that require those things: stability, that need stability, have volatility, and need fast iteration. And don't care about order. It's just a pile of stuff, like games. It came originally from the gaming industry, this particular, the Colony project. But this data structure has been used by a number of industries for a long time. I can't tell you what they all are, but a couple of examples are particle simulation, which is kind of like a game, but with a whole lot more bad guys. So I understand. I'm neither a gamer nor a particle simulator, but financial data manipulation, they always need stuff go fast. So it's a general purpose container. I say this because I think for a while I was kind of thinking, well, this is for gaming. This is for gaming. This is not just for gaming. So we have this reference implementation, and I'm just going to give you a couple of quick details because it's kind of interesting. It's an intrusive double-linked list of blocks, but the blocks hold the elements, of course, but they also maintain a free list internally. And the reason they do that is so that the free list can be indexed instead of using pointers, so that if your block size isn't too big, you don't need to use 8 bytes for your pointer. For your index, you could use 2 bytes and save space. And they also maintain this thing called a skip field. And the skip field is there to allow the iterator to have order 1 behavior, regardless of how many holes the iterator has to jump over. And that's very clever. And I'll show you'll see how that's done. If you use a bit string to represent the elements that are missing, it's not, or it's arbitrary latency, because you have to count some number of bits and you don't know how many that's going to be. This uses a different scheme, so you always know where to jump, and it's always order 1. And I believe, yeah, I'm pretty sure that the other thing is that the bit solution requires a branch, and this solution does not require a branch in the iterator, at least not to do the skipping. At some point, you're going to have to notice that you're at the end of the container, but so let's look at it. Again, I think the pictures are always worth a lot of babbling. So it starts out empty, just like all containers. We get one element, we have a skip field. Right, we add some elements, they're going to add some more elements, got another block. All right. And now let's see what happens if we erase. Erase an element, okay? That goes on the free list, which is this sort of slightly complicated structure where you have a linked list of blocks with free elements, and then within the block you have this encoded, index encoded linked list of free elements. And your skip field, which says 1, jump 1. Okay, let's delete another one. All right, see, we're adding to our linked list of blocks. Now we're going to add to our internal linked list, and notice now it says 2, so we can iterate in either direction and know how far to jump. And there's more to this. I'm not going to go in, you'll hear me say this a lot. I'm not going to go into the details, but the author of all this, I've got 3 links, a link for a paper and 2 YouTube videos from the author of this that are great if you want to know more. Right? And now let's add some more elements. Well, we're going to start at the head of the free list, boom, right? And then boom, boom, boom. Make sense? Pretty cool. Yes?
Sorry, I didn't quite understand the skip field. That's not per element, is it? You've got like one long block.
I sorry, I didn't quite hear you.
I don't quite understand the skip field.
And the skip field. So if you need to, so the iterator is coming along.
Yeah.
It says, okay, I'm here.
Yeah.
Now I'm going to plus the iterator.
Yeah.
It says add 2.
Well, hang on a minute. So what does it? It checks something, does it, to see whether or not it needs to skip?
Well, these are
2
zeros.
elements?
Actually, I should have put them in. It always adds this number. There's
right.
no branch.
So every element has a field.
Yeah. I've only put in the ones that were interesting, but this is a 0.
I understand.
So it
the
adds
skip
0.
field is actually a number of blocks.
Or I should say, yeah.
Yeah. Okay. Cool.
Yeah.
I'm with you. Thanks.
Exactly. So it's going to advance by 1 plus this number. So 1 plus 0 is 1. 1 plus 2, right? I should fix the slide to do that. Yes. Back there.
When deleting a block, if you need to update the skip field for the adjacent entries, like how is that constant time?
You're saying if the block is empty and it gets deleted?
No, sorry. Like if you have an element, if you have an element and you delete that element and it's surrounded by like empty like elements, then you have to update the skip field for those as well, right?
That's right. And I didn't show that. And it's very clever. The numbers in between here, if this is longer than 2, they're not irrelevant. They'll be like counting up to this number, and it uses that to do order 1 deletion.
Thank you.
Yeah, the question was, Why is deletion order 1? And the answer is read the paper / watch the video, because it's very interesting and very clever and very well described, and I'm not the right person to teach it. All right.
When you insert things in place. Running back.
Hello. Right. So you're inserting elements into the Hive. And when you iterate over them, what order are they in? It looks as though they are just in random order.
Random order.
Okay.
Order's not maintained. Yeah, this is not an ordered container. It is a sequence, I guess, in a sense, but there's no maintained order. Okay. Node-based sequence containers, list and forward list. We should probably, I think we understand this at this point, right? Every element is in its own memory allocation. So you have a block size of 1. This is very high overhead for small elements. Poor iteration, right? Because it's randomly accessing random locations in memory. That's the worst possible situation, because the locality of reference is terrible. Worst possible situation. But there's some use for lists. Just one little note here. The names are a little confusing if one were coming from somewhere else than C++. List is the double linked list. Forward list is what I always learned back in the day as a linked list, or if you prefer, a single linked list. It's just what the names are. You get order 1 insertion and deletion anywhere, guaranteed. You get maintained order. You get perfect stability. Nothing ever moves. You get mostly order 1 splicing. Why don't you get, it took me a minute to remember this when I was writing this slide. Why don't you get order 1 splicing all the time? Because the container has to maintain a size field, because the size function is specified for all containers in the standard library to be order 1. The only way to have order 1 size for a linked list is to maintain it. So if you splice in an arbitrary, 2 pointers that contain some that point to some arbitrary chunk of list, you have to count it. That's order n. But if you're splicing in one thing, it's order 1. Perfect stability comes at a great cost. But, for large, if you've got huge things or things that just cannot be moved, then it's a great solution. Your things are not going to move. You can in place construct them on the spot. They will never ever move until they're destructed. You can splice if you need to move. If you need to move them to another list, you can splice. So it does offer functionality that is certainly useful. Just don't think that, oh, well, I can push the front and back, so this is going to be a fast way to do that. Depends, as we've seen. This is CS 101, right? You got previous next pointers, head and tail pointers, size field, right? I'm not going to dwell on this unless someone sticks a hand up and says, no, explain. Oh, someone stuck a hand up.
Just a single list. With a single linked list and forward list, there is no size field.
Oh, forward list. We're about to get to that.
Right. Okay.
Yes, this is list. Forward list is very much like list, but with only one pointer and no size function, because no size field. And that was the question, or the comment, that there's no size field in forward list. That is true. And the reason is that the design goal for forward list is right there. That quote is out of the standard in the top section of forward list. This is supposed to be equivalent to a handwritten C-style singly linked list right out of the standard, okay? And it looks like this. No size field, one pointer. Boom, boom. Okay, so if you want this for some reason, you got it. It's hard to imagine lots of uses for this, but there are some.
Doesn't fit the conventions of the SDF because the names of things are like insert after and like so
That's right.
Yeah, what I said is it doesn't fit the
Yes.
conventions of the STL because the names of all the mutating functions are all something after because of.
That's right. That's right. It doesn't, if you have A, B, C, and you insert something at B, you insert X at B, you're going to get A, B, X, C. Whereas for list, you're going to get A, X, B, C. Because, it can't, it would have to go back to the beginning and it would be order n to insert otherwise. All right. Now we get to talk about something pretty interesting. Container adapters. I'm not sure I've ever used one of these. They've been sitting there. I just sort of ignore that, container adapters. These things are actually pretty cool. Okay. They're wrappers around containers, and they provide a particular, what's the word I want? Front to the, no, that's not the word. What's that? Facade. Thank you. That's having a moment there. A particular facade to containers, and they're great. You have to remember a few things, though. First of all, they own their container. They don't reference yours, which means that getting stuff into dealing with your container and it becomes a little bit tricky, and we're going to see that in a bit. But by moving into them, you can get some of the behavior you might want. They also have specific requirements. They call certain things on the containers, and if those things aren't there, they don't work. And we're going to see, and we've already seen the problem with this. We're going to return to it in a minute. So we got a stack, a queue, and a priority queue. So stack works with vector, list, and deck. Cool. Defaults to deck. Queue works with list and deck, but not vector. We've already seen this. Defaults to deck. And priority queue works with vector and deck. Priority queue can't work with list because it maintains the heap internally. That's how it works. At this point, you might be thinking, well, wait a minute. Queue. Quite likely want to have a little queue of little things like pointers and only a few of them and have it work really fast, right? Well, we know what container we want for that. What container do we want for that? Vector. Oops, sorry, can't have it. Your ire should be rising at this point. I think we have to go back to another misdirection interlude. Vector does not have front operations, so you can't use queue on it. And deck and list are both poor choices if really what you want is a little fast queue. And you can't use in-place vector, which would really be nice. Because then, there could be some really great applications to that. But no, sorry. Another thing, you might have noticed that the stack defaults to deck. Why is that? I mean, again, the only reason you'd want to use a deck would be if you are going to have this huge stack and you're worried about filling memory or something. Otherwise, why wouldn't you want a vector? Surely that's better. And also, people use defaults. Wouldn't you just tend to write this? This gives you a deck and all that machinery and allocations and stuff behind the scenes. You might not have even realized what's going on. Yeah. Don't know why, but it probably should have defaulted to vector, but that's been that way for a long time, since like 98 anyway, I think. So we're going to go quickly through the associative containers because they don't really offer any, they offer a little bit of stuff to talk about, but fundamentally they're node-based containers. So the fundamental memory behavior is the same as something like a list. But, and I assume everyone is familiar with this. We've got maps and sets. Maps store a key and a value, sets just store a key. We've got the multi versions and the unique versions, or the plain versions. We've got ordered and unordered. Unordered, as I think John pointed out yesterday, is what everyone else calls a hash table. If you want to know why it's not called a hash table, go watch his video, video of his talk yesterday. He described it quite well. I wasn't going to go into it. And they're all node-based, including the hash tables, unordered ones. Which might be a surprise to people who use hash tables that it's node-based. But the requirements that the standard library imposes on containers require that it be node-based because of the invalidation requirements. So, and we'll see what it looks like in a minute. Okay, and maps and sets are the same thing. If you've ever looked at it, it's the same code. Just, you know, you have a key or you have a key value pair. The ordered versions are search trees. The unordered versions are hash tables. I don't think this is really adding too much. Oh, all of them support splicing and rekeying and other node manipulations. This is since C++17. I'm not going to go into that today, but I linked a talk of mine where I do describe that and what the things you can do. So this is kind of new. C++17 is fairly new. You may not realize that. It's kind of cool.
Question?
Yeah.
Yeah, there's a question from an anonymous online attendee. I think there is an issue with stud list move constructor not being no accept. Is that an issue? And if so, do you have recommendations on using lists due to this issue, to the issue?
Can you tell me what he said?
I can repeat.
Constructor for list, not well accept.
Oh,
It's not part of the standard well accept. Some of the implementation to, well, Microsoft implementation is not.
does not have no accept. Yeah.
There's a lot behind.
There's a lot behind that. That is not something I have time to talk about today. And I would have to go back. I have, at one point I did know the answer to that question, but I probably would have to go back and talk with a couple of people to have a proper answer. So send me an email or something, and it's too long to discuss here, and I'm not sure I can do it off the top of my head. All right. Move constructors should be no accept. All right. Where were we? So set. The real issue here is you want an ordered list of numbers. You use a set, right? Well, remember, you're getting all this incredible pessimization for the convenience of a set. Although, hold that thought, because we're going to come to something in a minute that's very good news. But if you use set, you're talking node-based container. So if you just have some local little thing, it's going to be much faster to fill a vector, sort it, and then binary search it. Set's going to look something like this. Again, this isn't a tutorial on how to write a set. just to give you an idea. All right, you've got some pointers. And I'm going to just jump ahead and show you the map one. You'll notice it's exactly the same, except with some extra stuff, because they are, in fact, exactly the same. A map is nice. It gives you order and log n insertion and lookup. It creates a dictionary. If you don't care about performance, sure, use it. But hang on. Quickly, unordered map. I think we've really covered this. A hash table really can provide much better performance, though, than a search tree, because lookup is going to be roughly order 1, assuming your hash function is good and you don't have too many collisions. However, this is a key point. The standard library hash containers are notoriously poor. And the reason for this is that we don't like to change C++ ever. So the API or the ABI, which means that something, when the state of the art moves along and you can't improve something without changing the API or the ABI, it doesn't get changed. And so honestly, you might try these, but if you know much about hash tables, you probably have a better one. The ones in the standard library are not the greatest, but they're there. And they look very vaguely like this. Point being that there's linked lists, double linked lists, not some other more efficient structure because of the requirement not to invalidate pointers and things. Okay. Now the good news. I saw these things and I didn't even pay attention. And then when I started looking into these, I realized these guys are great. These are the flats. These are new in 23. And they wrap 1 or 2 sequential containers, contiguous containers like dec or vector. And they provide map and set behaviors for you. So you don't have to do it yourself. You don't have to fill a vector and then sort it and then search it. They do it for you. And these guys, they work with vector and dec and in place vector. They default to vector like they should. And I think they're just going to be absolutely great. There's a couple of things you need to know about them, but for a lot of uses, these are going to be superior to the conventional map and set. And they're all there, all 4 of them, as you see. So what are the gotchas? You might want to preload and pre-reserve the containers. You can do that. Just move them in. Okay, because remember, adapters maintain their own copy. So you got to move into that copy. Okay? Easy to do this. But what happens if you want to reserve later or call shrink to fit or something like that? That's a lot less obvious. That looks like this. So you have to extract the container. I think I got a pointer here. Ah, there we go. You have to extract the container. Notice that this that extract is a R value qualified function. You have to call it on an R value. So you have to call move on your set and then call extract. You can then do whichever you want to the container, and then you can move it back in with this function called replace. So when I first realized this is what you had to do, I got kind of nervous. This felt like, okay, I looked out my window and I see all these zombies in the yard. And then something knocks on the door and I go and open the door, right? Not a good idea. So I spoke to a library maintainer whose opinion I quite value. And he said, no problem. Replace restores the invariance. you're back alive after you call replace. So as far as I know, this is not UB or anything too scary. And you can do it with map, of course. You can do it with shrink to fit. Yep. All right. So I love these things. Use them. All right. Time for one more example. So I used to work for a digital map company, and I was extracting products from their GIS database. And it was a complicated database. And all these joins that we were doing in the database, or that they were doing, I should say, when I got there, were super slow. Their run took 3 weeks. Yeah, 3 consecutive weeks of computer time to run. So I realized it was much quicker to dump all this into memory and then do all the relations as pointers in memory, and it just ran a lot faster. So I used maps. And the key was the primary key of the table, and the value was, whatever row object I created that has whatever I need. And it worked great. And I got the time down from 3 weeks to 8 hours, which was, kind of game changing. And I was filling up memory very completely. I know this because I originally was working on a 32-bit computer, and I had to tell Windows, I want 3 gigabytes, not 2, for my process space. There was some magic way you had to do that, or it would only give you 2. And we had to do that to get the biggest tile, and the biggest tile was Texas. Okay. Because remember, this is a road database. The fact that Alaska is more than twice as big as Texas, Alaska has very few roads. So, and it worked great. Filled up memory great. But I wonder next time if, I wonder if I was leaving some performance on the table, and I wonder if next time I should do it a little differently, because I had this very controlled environment. And you can ask the database how big the table is, right? That's order 1. I didn't know that. And nothing is changing. I mean, this is a read program. It was reading the data and making stuff out of it. It wasn't ever touching these things once they're in memory. So I wonder if using vectors pre-reserved to the exact size and allocated, appropriately so they filled memory well, would have made for better performance. I don't know. But it certainly would have taken a lot less space, and smaller, right? Big, slow, smaller, faster. It'd be interesting. And of course, now we can use flat set and flat map. So which should I use, flat set or flat map? Quick quiz for something like this. Nobody? Eesh. Okay. Well, it depends maybe, but so if I have 2 vectors, which is what flat map uses, their locality of reference relative to each other is poor. They're arbitrarily positioned in memory. So if they're huge, probably doesn't matter. I'm going to be reading a bunch of pages off of each one. It probably doesn't make much difference. But if they're small, if you've got a relatively small map, maybe just do it as a set. After all, you can just put the key in the object somewhere and use that as your thing that you're sorting on. Then you only have 1 container and 1 read, 1 fetch from main memory. Something to think about.
Fewer keys in the cache. Yeah. That's the trade-off. That's why you like having it separate. Yeah.
Good point. It's a trade-off. But if it's all going to fit anyway, like if the whole thing is going to fit in the cache, then you're better off in the set. So it's about size. All right. We're to the final chapter. I'm going to talk about sequence, which is a proposal that was looked at about a year ago, just a year ago, by the committee. I just want you to know I'm a absolutely independent, objective, third-party reporter here. So sequence, I hate to say this. I don't want to say this. I really don't want to say this. You could think of it as vector 2.0. Oh, there I said it. I hate the term, I hate the name vector for all the reasons that John went into yesterday. And I don't necessarily want people to think of this as it's got to be like vector necessarily, but it is kind of vector 2.0. But it has 4 memory handling modes. Okay, local, we've talked about what I mean by that term. This is just like in-place vector. In fact, it's exactly like in-place vector. It is a drop-in replacement for in-place vector. It has variable, which you could also think of it as vector mode. I will never call it that on paper, which is just like vector and is a drop-in replacement for vector. There's 2 other modes. Fixed is like local, only allocated on the heap. So fixed size, but allocated on the heap. I think there's a number of things that could be quite useful about that, especially since it reduces the size of the, well, as we'll see in a minute, it reduces the size of the object itself to 1 pointer. And buffered, which is small buffer optimization, just like clump or boost small vector. So let's look at these real quick. Again, same pictures. This is just like in-place vector, should be no surprise. That's local. Here's fixed. Notice, same exact thing, just out on the heap with 1 pointer from the sequence object. This ought to look familiar. It's the same slide as vector. And we have buffered. Now, in this case, we're in the buffer, 3 elements with a buffer size of 4. Flagged, we have this extra field to tell it whether it's buffered or not. Or we have a block like vector, pointers like vector, and the flag says dynamic. Because of these, sequence subsumes vector and in-place vector. Yes, the timing's unfortunate. It would be nice if I could get in my DeLorean and go back a few years so that we didn't have to do in-place vector, but don't get me wrong, it's really great that we have in-place vector. I'm really glad that's in there. And clump, the reason I'm not really talking about that is it's exactly the same as what we're talking about here for sequence. If this goes, we won't need clump. If this doesn't go, then clump with a hopefully adjusted name will be something that I hope we actually do, because we really do need this behavior, small buffer. It does not have a vector bool specialization. Cue applause. Thank you, thank you, thank you, thank you. In fact, if you say sequence bool, you get a sequence of bools. How odd. It has this other thing. You can adjust the size type. This is kind of nice. Now, this can be done automatically. Actually, the in-place vector that I was looking at did this automatically. But I think it's kind of nice for the user to be able to do this, because you might want your size, let's say you're only going to be putting, 31 things into your, you want to use a size of 1 byte, right? But what if what you care about is maximum speed? Well, you really might want your size field to be a word. And only and different computers have different word sizes. So the user gets to specify the size field type, or if you will, the size. And remember, well, we're going to see in a minute, sometimes you have 2 size fields. Okay. The 2 modes that have growth, which is vector mode and buffered mode, you get to control the growth. You can do it linear, by a user-specified size, or exponential by a user-specified factor. So you get to control that. You can tune it. I added this other one, vector. So this is there in case the library, their vector has something that can't be modeled exactly by exponential alone. I mean, I don't know if this exists. I don't know if this is necessary, but if we leave it in there, it lets the vendor exactly duplicate vector's behavior so that vector can be defined in terms of sequence. Also new and different is that there's 3 element positioning modes instead of 1. Front, like vector, back, like nothing that's in the standard library but is potentially useful, and middle, like deck and an actual double-ended queue. So let's look at those. So front, okay, no surprises there, right? That's vector. Back grows up this way, yeah. Middle, we start in the middle, and then we go where we go, but as we start deleting and adding, deleting, adding, deleting, now what happens when I add one more? It shifts. In fact, Jonathan Wakely turned me on to this, and he calls it a shifty vector, which I thought was an excellent name. Excellent name. So, well, there was, sorry. There was a complaint. Yes.
I have a question about this shifting mode. Why wouldn't the wrapping be preferable? Because then you wouldn't have to move stuff that is already there. Like if you go back to the slide where you had this middle mode and it filled up, and if you add now one more at the end, why couldn't you put it in the beginning of the block and do like a circular buffer?
Oh, because it's an ordered sequence, just like vector. That would make.
But if you already have 2 size fields, like a beginning and end of the used part of the buffer, then you can also, if the used part is at the end of the buffer and you want to still append, you can wrap around, and the beginning shows to the first used element, and then the end shows like has a smaller index value, but logically is after.
Okay, but how would you iterate that?
Start from the beginning and step forward. When you get to the end, you wrap around until you reach end.
Yeah. So the problem with that is that the elements are no longer mutually consecutive. And this is a container that one of its invariants is that the elements are always consecutive, just like vector. They can't be split into 2 pieces.
Okay, if this is a requirement, yeah.
It's just, Anyway, but yeah, that can be useful for things, but it's not this container, because that would violate the performance kinds of things we're looking for. You definitely would not be as fast to iterate if it had that behavior. So anyway, one of the objections that was raised by the committee was that this is just too complicated. The poor programmers are not going to be able to handle this. To which I said, hooey. First of all, C++ programmers are smart. Of course they can handle this. And second of all, if you can run a 70s stereo, you can run this. Okay. Oh, so this, I shouldn't have used their laptop, your laptop, because the font that sequence is in, I got the right font, like the Marantz font. And so, oh well, I'll remember that for future. If you run it on my laptop, it gives you the right font up there. All right. few other features, front and back access functions. The whole API is always available, okay, regardless of any of these settings. Yes, thank you. And I'm heading right for it, so. The fixed capacity, you may say, well, okay, that's used for local mode, fixed mode, and buffered mode. Buffered mode, it describes the size of the buffer. What about vector mode, variable mode? In variable mode, it describes the size of the initial allocation, the initial block. So the initial capacity. And this is really cool because it's a common pattern to declare a vector, immediately reserve it, and then go use it, right? The problem with that is it's not lazy. You always have that allocation. What if you never put anything in the vector, right? This means you don't have to remember to do that, and it's lazy. You won't actually get that allocation until you put something in the vector. So, and
Well,
no.
If your capacity is greater than your current,
If your capacity is greater than your current size and you add an element, it's guaranteed not to allocate. But if you're saying the capacity is where I'm going to allocate the first block, but I haven't allocated it yet.
No. The fixed capacity, which is a compile time user input to this. That's not the capacity. When you call capacity, you get what it
Okay,
depends.
okay, I see what you're saying.
Okay. When you call capacity on a fixed or a local, you get the fixed capacity size. When you call it on a variable, you get whatever the capacity is at the moment, just like a vector. And by the way to tell whether you have an allocation or not is to call capacity. If it's 0, you do not have an allocation. We'll come back.
While I have the mic, I wanted to ask you one question. That the small buffer optimization that you have here, can I affect that with a template parameter? Is that a compile time adjustable thing where I can say,
It's the same. It's the same value. It's the fixed capacity setting. That's what's one of the inputs. One of the template inputs. This template has a lot of inputs. They're in
part of the stereo.
Absolutely part of the stereo. You'll notice that the increment goes up to 11.
Yes.
And you know why.
Yes.
Okay. You can reserve in any mode, which is nice. That lets you force fixed mode to allocate if you want, just like variable mode. But you will always get the fixed capacity size, not what you pass to reserve. If you try and reserve greater than what it can do, it'll throw. There's a free member. I've just recently learned that people actually have been asking for this. It just does clear and then shrink to fit so that it actually frees the block. And there's an isDynamic member. This tells you whether you're on the heap or buffered in the buffer. It's not particularly useful for the other modes because it's constant. It's always the same for them. In particular, this is not how you determine whether you in fact have an allocation. For fixed, it'll always say true. All right. Quickly, because we're running out of time here, but motivation. There's variety here that isn't available. Much more importantly, there's flexibility that isn't available. And you can tune. So you can write your code, use this thing, set it up in some way, run it, see what happens, tweak it, run it, see what happens. And you don't have to change your code or compromise your code to do that because you're not changing between vaguely different APIs and things. You're just using the one thing that does the same thing with these adjustments. It also has some improvements that we can't make with Vector for the aforementioned reasons because we don't change things that are already out there for good reasons. Like front operations. It has front operations in all modes. Sure, exactly, because it's misleading. And also, but much more importantly, you want to be able to use Q on this, and you can. It works great with Q. Middle mode is great for Q, and it works great because it has front operations. If you want to use Q on a deck, go ahead. But if you want it to go really fast, or if you want it to be local, use sequence. There's an interesting irony about deck, which is that the map, the thing that, that's really a list of pointers to the blocks, is often implemented as a double-ended queue. So deck is implemented with a deck, and you can use sequence in middle mode and would be perfect for that. Flat map works with it. And we know there's uses for in-place vector and for a vector with SBO. People have been screaming for them. There's proposals, and in fact, we have in-place vector. Now, I realize that's an argument for and against this proposal, but that's another story. I got a bunch of links for related talks, for Hive, for deck, for clump, for sequence. And that is how I suggest that you choose and use the right container for C++ and beyond.